A square number is simply an integer multiplied by itself, but physically it represents the exact area of a perfect square with a side length of n. When you need to square a decimal, like 2.5, you can temporarily ignore the decimal point. Treat it as 25 times 25, which gives you 625. Because the original number had one decimal place, squaring it means you count 2 places inward from the right. Drop the decimal there, and you get your final area, 6.25. This is why memorizing your base squares from 1 to 20 is so valuable. It strips the difficulty out of decimal math, turning calculation into a simple matter of formatting. You can spot a fake perfect square without doing any math just by looking at its last digit. Perfect squares can only end in 0, 1, 4, 5, 6, or 9. They never end in 2, 3, 7, or 8. The same logic applies to zeros. Take the number 4,000. Because it has exactly 3 trailing zeros, an odd number, it cannot mathematically be a perfect square. Checking the last digit and counting zeros acts as a rapid filter. When you're under time pressure in an exam, you can immediately eliminate impossible answers before you write down a single equation. Squares also hide a direct connection to odd numbers. The square of any number n is exactly equal to the sum of the first n consecutive odd numbers. 1 squared is 1. 2 squared is 1 plus 3. 3 squared is 1 plus 3 plus 5. But what if you need to find the sum of a sequence that doesn't start at 1? For example, adding up the odd numbers specifically from 11 to 19. Instead of adding manually, you use the subtraction method. Take the square of the entire sequence up to 19, which is 10 terms, and subtract the sum of the unneeded first 5 terms. 10 squared minus 5 squared gives you 100 minus 25, leaving exactly 75. Because of this sequence, the difference between any 2 consecutive square numbers will always result in an odd number. Understanding these algebraic patterns simplifies multi-step addition into a predictable single-step shortcut. When we move from squares to cubes, we step into the third dimension. A cubic number is an integer multiplied by itself 3 times, shifting our math from measuring flat area to calculating physical volume. This introduces a specific challenge when dealing with negative integers. Let's evaluate -12 cubed. Following the sign rules, the first 2 -12s multiply to create a positive 144. But multiplying that by the third -12 flips the final product back to -1,728. The dimensions scale up, but the rules remain strict. Tracking your negative signs and memorizing your base cubes are the most reliable ways to master cubic numbers without getting lost in the arithmetic. A cube root acts as the reverse engine of a cube. Finding the root of a complex decimal, like -0.000216, can cause cognitive overload. Bypass this by converting the decimal into a structured fraction. Rewrite the problem as the cube root of -216 over the cube root of 1,000,000. Solve the top and bottom independently. The numerator becomes -6, and the denominator becomes 100. Divide those out, landing cleanly on -0.06. Converting decimals to fractions separates the math from the visual clutter. You take one impossible-looking problem and turn it into 2 simple, memorized roots. This level of numerical fluency defined Srinivasa Ramanujan, the mathematician famously associated with the number 1,729. Today, this is known as a taxicab number, the smallest integer expressed as the sum of 2 positive cubes in distinct ways. Look at the number 4,104. It proves this property perfectly because it equals 2 cubed plus 16 cubed, but it also equals 9 cubed plus 15 cubed, 2 distinct cubic pairs resulting in the exact same sum. Ramanujan's legendary intuition was rooted in his daily familiarity with these numerical properties. Memorizing basic cubes up to 15 provides that same tactical advantage, making it possible to recognize these patterns as you encounter them.